Vlatko Vedral, welcome to Bendiksen Airways.
Thank you very much. Pleasure to be here.
Nice. Can you tell me the difference and also explain what gut is and toe is, as in the grand unified theory and the theory of everything?
Good question. I think these are still imaginary entities in physics, so we do not really have a grand unified theory, or it could be the same theory, actually, a theory of everything. The main reason is that, at least at present, we may find out that there are many more problems to worry about. But at present, we have gravity, which is the only force out of the four fundamental forces that hasn't been quantized. So everything else is really subject to quantum theory. The electromagnetic forces, the strong and the weak forces, and we have gravity where um, there are some mathematical issues related to this, but primarily the problem is lack of any experimental evidence telling us which way to go. Now, it's fair to say that even if we did figure out what to do with gravity, it's very questionable. You could call this a grand unified theory. You are right. That's certainly appropriate. But whether this would be the ultimate theory of everything is really anybody's guess. It's not even clear. I think it's a nice vision to have that we are getting deeper and our knowledge is encompassing more and more of our reality, if you like. But I think it's not even clear that we will ever get there. So it's more like a dream for a physicist than reality at present.
Before we dive deeper, how would you introduce yourself?
Probably as a quantum physicist first and foremost. I think I've worked on many different areas really related to quantum mechanics. I started with quantum computers. So I think when I was finishing my undergraduate degree, an algorithm came up, Shor's algorithm, which actually surprised everyone because Shor showed, in fact, that you can compute some things exponentially faster on a quantum computer than a classical computer. And that excited an awful lot of people. So I went in and I did my PhD in this direction in quantum information. But then what ended up really fascinating me the most is this relationship between information and physics in general. And in fact, information and science, it goes even far beyond physics. So I ended up actually using information theory to understand quantum entanglement, which is the effect that Schrödinger called the characteristic trait of quantum mechanics. So ultimately, I really stayed more within physics. And for me, it was always a question of what can we learn about physics by phrasing it in terms of information. I think that's maybe my main activity.
I just recently read Something Deeply Hidden by Sean Carroll.
Yes.
He speaks a lot about that quantum mechanics is something that not enough are really looking at, and that it's kind of frowned upon. Is that correct?
Yes, there are so many opinions around. I've promoted this idea that at present it's of course incredibly successful. And I think what's frustrating about quantum mechanics is that it's really difficult to anticipate where the theory could fail. So in fact, these are the experiments we should be looking into. And this is where people disagree. Gravity, obviously, as I mentioned, is an obvious potential culprit because we don't have a quantum theory of gravity. And in fact, some of my colleagues are betting that gravity will even collapse quantum mechanics and end entangled states. All of these quantum effects will ultimately, when they encounter gravitational forces will collapse. We have no experimental indicator whatsoever. So it's really frustrating that the more we go into the macroscopic domain, so quantum theory started as just as the need to understand tiny systems, atomic spectra in particular. But we made a long way because quantum physics then went into many body physics, into larger and larger systems, solids, liquids, gases. All of this requires quantum mechanics to be explained, stability of matter. And now people are even looking into chemistry, going further into biology. There are people claiming that entanglement even may matter in biological processes and living systems. So it really makes you wonder, is it really even a universal theory? Is it possible that quantum mechanics is the final word and we simply just have to tidy up and understand these more and more complicated systems? Of course, the other view, as you mentioned, is also possible that there is surely something coming after quantum mechanics, that in fact, and I think it's a very credible view, that the reason why we are struggling when it comes, for instance, to understanding gravity, or when it comes to even bridging the gap between inanimate objects and living systems, it's credible to consider that this is because we don't have the ultimate theory of physics, that there must be something that's coming beyond quantum mechanics. It's very difficult to tell at present. It seems to me, just my own personal perspective, is that we have zero evidence for that view, and that we should really keep pushing into the more complex domains and really just see and try to test whether anything ever goes wrong. And I think that's the first time, if anything does go wrong, that we will have some experimental reason to modify quantum mechanics. But I think at present we have no reason to do so.
So when you say that gravity is not quantized, what does that exactly mean?
Yes, that's a good question as well. Um, so what it means to quantize something is really to acknowledge that this goes way back to Heisenberg, I should say, the first, what people consider the first proper introduction into quantum mechanics, 1925. So the first maybe proper paper defining what quantum mechanics should be. So what he did is he made a really revolutionary claim there. And the claim is that the laws of classical mechanics, laws of Newton, I think this is what he was worried about at that time. But the same can be said about gravity or any other aspect of classical physics. He said that the laws of dynamics, how things change in time, if you look, for instance, at a particle and how the position of a particle changes in time, Heisenberg claimed that you don't need to change this law. The law itself is fine, but the entities that obey the law should not be the ordinary real numbers. Dirac called them C numbers, classical numbers. So, for instance, when we measure a distance that something traveled in, usually you say something like 5 meters. It's 5 meters away from the initial position. Now, Heisenberg claimed that you can't anymore do this. In order to explain how atoms behave, Heisenberg said we need to upgrade these C numbers, the classical real numbers, into what later was called quantum numbers. But they're basically matrices. So what Heisenberg decided is to assign many rows and columns, basically a mathematical entity that's represented by a matrix, and this should now signify the position of a particle. And the same he did with speed of a particle, with energy of particles, and so on. And what he then discovered subsequently is that now it's quite interesting because the rules of multiplication now change. So, for instance, in classical physics, if you first specify the position and then you specify the speed of something, it makes no difference if you invert the order in which you do this. So whether, practically speaking, whether you first measure a position of a particle and then the speed of a particle, it will give you the same result if you reverse your measurements. But Heisenberg discovered that if you now use these matrices, if you use quantum numbers instead of classical numbers, you actually have to worry about which order these measurements are made. And that's the famous Heisenberg's uncertainty principle. So now, once he discovered that, and once this was confirmed for atoms, then in the electromagnetic field, what this means for the gravitational field is that there are certain things that you cannot measure at the same time in the gravitational field. There are components of the gravitational field that behave very similarly to how a position and the velocity of a particle behave. Remember, in Einstein's theory, which is the most accurate description of gravity we have, in general relativity, everything is described by real numbers, by classical numbers, and everything in Einstein's theory can be measured at the same time. There is no contradiction there. If you were to quantize gravity, what it would mean is that you could measure certain aspect of a gravity very well, but then it means other aspects of gravity you will not know at the same time. And we are still debating what this means. It's not entirely clear what this means, because if you talk to different researchers, they would actually tell you that different entities should be quantum in this theory. So we don't even have an indication of what this could be ultimately.
Is it true that we have not yet observed a graviton?
That's right, and that's a good point there, because um, not only have we not observed it, but because it's a very weak force, there are many well-regarded physicists who actually claim that we will never be able to observe it. So, for instance, Freeman Dyson wrote a sequence of papers starting maybe 20 years ago or so, where he did very rough calculations. For instance, when you excite an atom and the atom now loses energy, what normally happens is that it emits light, it emits photons. But there is a probability that it also emits a graviton if quantum gravity is a correct description. And what Dyson did is he calculated the amount of time it would take an atom to emit a graviton. And it turns out to be so long, much longer than the age of the universe. So basically, we simply don't have the time to wait to detect the graviton. And in fact, he analyzed various other schemes, and he either run into trouble with the amount of energy you need for this, or the amount of space, how fine you have to discriminate different distances, or the amount of time that's required for the whole experiment. And actually, he ended up claiming that we may never need to quantize gravity simply because the consequences are unreachable to us, experimentally speaking. So that's yet another view on this problem.
And why does it feel like a strong force for a human and but it's so
Good,
weak?
excellent point. Yes, for us, actually, it looks like a dominant force. And in fact, that is to do simply with the sizes of the objects. It is a weak force. And so if you look at, for instance, two atoms, then of course the electromagnetic force is many, many orders of magnitude stronger than gravity. But because we are sitting on Earth, and because of what matters to us, of course, is the gravitational effects of even the moon, for instance, on the tides, certainly of the sun, and other astronomical objects. This feels to us like a very strong force, as you say. But if you compared the equivalent, if there was the electromagnetic equivalent, it would be it would be 40 orders of magnitude stronger than the gravitational force. And that's actually exactly the challenge for us experimentally, because the objects that we want to behave quantum mechanically and the objects that we can control quantum mechanically are usually very small. Therefore, the gravitational effect that they have is also very small. So the question is, can we find a sweet spot where both gravity and quantum mechanics can be maintained? So it mustn't be too big because quantum mechanics could then be extremely difficult to observe, but it mustn't be too small because then gravity becomes very small. And this is extremely difficult, this problem. And there are various ideas there how to try to circumvent it.
So what you're saying is that we won't observe a graviton. That's more
This
or
is
less for
this is
certain.
one this is one conclusion that we will not observe graviton. What I did with a while back with a few colleagues of mine is to suggest an indirect way of measuring um, the quantum components in the gravitational field without having to detect gravitons directly. So that's possible. We could perform measurements where we know that gravity must have some degrees of freedom, which are quantum, but at a higher level from just observing individual gravitons. And I think this already would be a nice indicator that that's the right thing to do. Because remember, we are not even sure whether we should be quantizing gravity. Maybe it's okay to leave it at the classical level. I'm personally against this view simply because it leads us to all sorts of inconsistencies. So, for instance, just to give you a simple example, if you believe that energy is conserved in physics, that you can never create energy or destroy energy, then it's extremely difficult to conserve it if gravity is classical, but anything else in the universe is quantum mechanical. This kind of hybrid version of putting two theories together never works properly if you want to satisfy all the principles that we believe are correct in physics. So, but this, you could argue that this is, of course, a more abstract and more mathematical reason, maybe, to suspect this. It could be that nature doesn't conserve energy in the way we think that it does. So even that's possible. But I prefer to think that things are conserved exactly in nature, and this somehow forces me to think that gravity ought to be really quantum. It's just a question of how to set up an experiment to detect this.
Remember in the book I just mentioned, Sean Carroll says that we shouldn't differentiate between classical and quantum. We should always think quantum because everything is quantum. What
Yes,
does
I
that
agree with
mean?
that. Yes, I agree with that. I think in my recent book, I promote exactly this view that everything in the whole universe should actually be subjected to this kind of Heisenberg's uncertainty. And that's independent of how complicated or how macroscopic the object is. Um, so, um, so the question then arises, and I think this is where people potentially disagree. The question arises how to understand classical physics. Why do we, for example, feel that things that matter to us are perfectly well described by Newton's laws? Why when we travel to the moon, why do we never need to use quantum mechanics? Why do we never take into account any of these extra effects? And the answer is very simple, of course, because they are very small. They are, even though they might be there, they become harder and harder to discriminate from other effects when the object becomes larger and larger and more complicated. So I think to me, quantum mechanics never disappears. I agree with Sean Carroll on this one. I think that quantum mechanics is, you should think of the whole universe as quantum mechanical. But then in some regimes, um, it so happens that classical physics is sufficient. But it doesn't mean that what you're studying is not quantum mechanical. It just means that most of it is perfectly well described by Newtonian dynamics.
Do you think there is an objective reality? And do you think we see it or
Good. That's
not?
also it's a very deep question for a scientist in general. I like to think someone called me the other day a Q number, quantum number realist. in the sense that I think we should take these entities that physics tells us about seriously. So, for instance, when Michael Faraday came up with the idea of a field um, to describe how forces between two charges propagate between these charges, so he had to invent a medium that exists everywhere in the universe, which he called, postulated basically, called it the electromagnetic field. Um, uh, I think the best understanding of all of these phenomena from then on was simply to acknowledge the reality of the existence of the electromagnetic field. Even though, I should say immediately, we never measure the field, the electromagnetic field directly. You never see a naked electric field or a naked magnetic field. All you do is put a test charge, you put an electron somewhere, and then you see how it responds. Depending on how it accelerates, how quickly it moves, does it rotate, does it curve, you can from this estimate what kind of electromagnetic field exists at the point where you put the electron. So it's always the responses of the charges that tell you about the electromagnetic field. I think it's very similar in quantum mechanics because so I believe that these matrices, the quantum numbers that describe everything in the universe, I'm a realist about their existence, even though, like I said, you never see directly a quantum number. You only see one of the aspects when you make a measurement. So whenever you make a measurement, you will always see an object in one place or another. You will never see it in many different places at the same time, even though quantum mechanics says that all objects are capable of being in many different states at the same time. So I'm a realist in that sense about these entities. However, it is difficult to imagine that we will ever know what the world really is like at that level. So if you really pushed me and you said, but do these entities really exist somewhere out there? Then I think it's perfectly possible that this is still our own abstraction. This is the way we understand these entities, but we may never even know what they are really like.
Mm.
So I don't know if that clarifies kind of my position.
Yeah, because I've dug deep into I don't know if you've heard of Donald Hoffman, but he speaks a lot about objective reality, and he makes the example of the oncoming train, for example. It's not a train, but you don't want to step in front of it anyway because you'll die. But he's talking a lot about that we don't see objective
Yes,
reality. I guess
yes.
that's a given, but do you think that space time is fundamental, or do you think there's something deeper beneath?
Good question. That's another very deep point, and it's related to. It's extremely important to ask that question when you're thinking about quantizing gravity, because it goes back to what you asked me earlier. What does it mean to? What are you actually quantizing? What are the entities that are becoming quantum when you do that? Um, there are people who believe that space-time is fundamental. And what they end up doing is they quantize different aspects of space and maybe even time, depending on your approach. So, for instance, there is an approach called loop quantum gravity, where, for instance, you claim that lengths and areas and volumes are no longer real numbers. They are not characterized by the conventional classical numbers, but they need to become quantum numbers, which is even difficult to imagine how this would work. But it would suggest something like this. If you want to measure the area and the volume of an object at the same time, you won't be able to do that. So classically, we know that if you give me an object, I can simultaneously tell you what the area of the, if I give you a pyramid, then I can tell you what the area of the pyramid is. I just add up all the areas of all the sides, and then I know simply the formula for the volume. But this is in classical physics. If this approach to quantum gravity is correct, then it would mean that you could no longer do that. If you know the area of something, you don't know the volume very well. Exactly the Heisenberg uncertainty principle applied to this. So there are people who take this idea seriously. I am more on the other side at present. Again, it's more my intuition. Like I said, we have no experimental evidence whatsoever which way to go. It seems to me that it's better to think about space and time as being a convenient fiction. Fiction in the sense that we physicists introduce a grid because it makes it easier for us to phrase our theories and to do our calculations. But it seems to me that everything can be done without reference to space-time. Space-time is probably in this picture something that emerges out of more fundamental entities than directly being there and being quantum mechanical, for instance. So I prefer to think of fields as being there and being quantum mechanical, and space-time being some kind of either a convenient grid for us or even some kind of emergent phenomenon. Um, and how exactly it emerges is again very unclear. There are many different views in that direction as well.
Because I've read some of Nima Arkani Hamed's work, and he works. I know he works with Hoffman
Yes.
on. He says that space-time is doomed, and that there are objects, or how you should call it, lying beneath space-time. He talks about the amplituhedron, etc. What does this exactly mean? What are geometries behind space-time?
Oh, this could be again one idea is this loop quantum gravity where you have to talk about some kind of discretization of space-time. So when you talk about these fundamental objects, you would be talking about, for instance, these pyramids which have exactly the smallest size that you can possibly have in the universe. So, in quantum mechanics, usually when you quantize things, they tend to become discrete, whereas classically they were continuous. So energy is discrete. The existence of gravitons is one of the consequences of this. Of course, photons as well, the particles of light, are also a consequence of quantization and the discrete nature of these things. So people think when you quantize space-time, if that's the right thing to do, you are looking for an underlying structure that gives rise to this continuous classical space-time. But actually, in the underlying picture, all you can talk about is quanta, different quanta of volumes, of areas, of lengths of different regions, even quanta of time, possibly, chronons, as people call them. So it could be that we are talking about the smallest unit of time that could possibly exist in the universe. And
Is that the
again,
Planck scale?
that's the Planck scale. That would be the best guess at present is that that's the Planck scale. But again, zero evidence for any of that at present. Yes.
Okay. So uh, we spoke about the uncertainty principle, and what do you think of the many worlds interpretation then? And does that, as I understood Sean Carroll in his book, that means that we don't have to take into account the strangeness of the collapse of the wave function because it's just branching into different universes?
Yes, I think it's my view is the closest to this interpretation. Maybe I object more to the language because it seems to me that it doesn't quite encapsulate everything that can happen in quantum mechanics. So I think when you say many worlds, you are still thinking about many classical worlds that exist at the same time. But actually, quantum mechanics allows all possible states, even in between. Anything between one world, classically speaking, and many different worlds exists also within quantum mechanics. So to me, I would say at least as far as I'm concerned, the best way to say it is that there is one universe, but it's fully quantum mechanical. And I think the closest interpretation is certainly many worlds. He's right that you eliminate a number of potential paradoxes. For instance, people talk about the special role of observers. Um, I disagree with that. I don't think that observers are needed at all to talk about quantum mechanics. And I think if you go in the direction of many worlds, you effectively eliminate eliminate in the sense that observers are not special in any sense. Observers are just like other physical systems. You eliminate the need for collapse, as you said. And I think also you find it much more easy to integrate all of these conservation principles that I was talking about. I think this is is the only interpretation at the moment, I think, that allows us to put all of these other principles together and phrase them in a consistent way, that they're all upheld at the same time. So to me, it has many advantages. There are no discontinuities, there are no collapses, there are no observers. All of the principles, conservations, the equivalence principle are upheld exactly in this universe. Of course,
Why are there
yes,
no observers? Why are there no observers if you look at the double slit experiment?
yeah, good
How
point.
do you then interpret that?
It's a good question. It's actually a very important point, and I think there is a lot of misunderstanding out there when people discuss these things. So, in order to destroy, it's an excellent point. In fact, that's the key aspect of that. Frequently, we talk about that the particle goes through both of the slits in this experiment, unless we look at it. And if you look at it, you will see that it goes either through one slit or the other slit, and then you will not see any quantum effects. There is no interference. I think this is true, but this mistakenly suggests that you need to look at it yourself. There is a much simpler way of destroying interference, which is the following one. And actually, the French physicist Fresnel describes this very nicely already in classical optics. So, what's enough is to have another degree of freedom, which changes depending on whether the particle goes through one slit or the other. Let's say we're talking about an electron, and the electron has a spin up or spin down state. Now, it's enough, for instance, that when the electron goes through one slit, the spin is up, whereas if it goes through the other slit, the spin is down. And this spin itself, it's only one bit of information now. The spin is telling you whether the electron is going through the left-hand slit or the right-hand slit. This one spin of information is enough to destroy the interference fringes. There is absolutely no need for us to observe anything. You can just simply collect all of the data, and you will then see that the spin itself actually is responsible for destroying the quantum effect. So when you talk about observers, it's very important not to give the impression that an observer requires complexity, it requires intelligence. It doesn't need to be even a computer. It's as simple as another quantum bit, if you like. And so long as you entangle this quantum bit with the relevant information, you will actually destroy superpositions and quantum effects. And I think that's all there is to it. That's basically how we can argue how classical physics, if you like, arises out of a universe that's fully quantum mechanical.
Is that a controversial view, or is that something most physicists agree on?
I suspect most physicists agree with this. I think they would agree with this statement. Where they tend to maybe disagree is that there could be other things that are capable of collapsing quantum superpositions. So this view that I told you about is called decoherence. And in fact, most people would say yes. What usually leads to the collapse, if you like, if you want to use that word, of superpositions, is the fact that these superpositions are now becoming entangled to the environment. They're becoming entangled to other degrees of freedom that we cannot even control. But this doesn't deny that everything together is still quantum mechanical. It's just when you look at the system on its own and you ignore all other degrees of freedom, the system suddenly starts to behave classically. So I think this is not controversial, but what is controversial is whether this would account for all collapses of quantum states. So there are people who would say, yes, we accept decoherence. However, there could be extra things that are happening at the same time. And at the moment, we have no evidence for that.
I have to ask about consciousness and if you think this has a place.
Consciousness, to me, fascinating question. Especially, I like this direction of the field that people call quantum biology, right? So, trying to really verify whether nature has evolved certain quantum computations and whether there was even an evolutionary pressure for some processes in living things to really utilize quantum superpositions, even entanglements and the full quantum dynamics. I must say, to me, I think there is quite a lot of evidence that this is the case. And I would be surprised, in fact, if nature didn't utilize quantum mechanics, because we know from quantum computing that you can do many things much more efficiently. You can store more stuff, you can do it more faithfully, you can compute things faster. However, when it comes to consciousness, we have no evidence so far for anything quantum mechanical there. But again, if you think about it, um, certain processes that are taking place in very small areas, very short times, to me, it sounds very natural that we should think about them quantum mechanically. Whether this is directly related to, let's say, our consciousness or even our subconscious, sometimes there are speculations that our subconscious information processing, it's really all to do with uncertainty. It's subconscious because we are exploring many different states at the same time. And as soon as we become aware of what we're thinking, that acts like a collapse in some sense of the wave function. I think this is an extremely interesting idea. What's difficult, it seems to me, is to come up with good experimental tests how to even verify whether any of this is true. But I think this is the future. It seems to me quantum mechanics will be going into more and more complex phenomena. And I think there are already a lot of interesting ideas in that direction. Quantum consciousness, which part of consciousness could be quantum even? Even if most of it is maybe not quantum, it could be that some crucial steps are really quantum mechanical. So I'm very open to all of this.
So, third, is there a possibility that consciousness could be fundamental, the objective reality we spoke about?
Oh, that's a good, that's again, my intuition goes in the opposite direction. And again, it's just an intuition that um, it seems to me that consciousness requires a certain degree of complexity and information processing ability. So I would even go so far as to say that not all living things are conscious, and I think that sounds intuitively correct to us. So clearly, the species that are closest to us, I think there is very little doubt that they have some degree of consciousness like we do. So probably most mammals, certainly apes are included in this. Most mammals, I would say, have certain um, aspects that are extremely close. Maybe they don't have the full range and capacity that we do, obviously, but I think they do have rudiments of our consciousness. If you go down this evolutionary scale, I think there is a cutoff point. I think it must be that there is an evolutionary point which could even be pinpointed more precisely, and I think it will be probably one day by biologists, where consciousness really starts to emerge. That there was some evolutionary genetic change that allowed for that. So that's why it seems to me if you go even beyond this and you go into inanimate objects, it seems to me that it's a big stretch to claim that they are conscious. I would be highly skeptical that this would ever go this way.
You've argued that information may be fundamental to
Yes.
physics. What does that actually mean?
Yes, that's also a very. I should. I should explain a little bit what I have in mind. Um, so uh, somehow in physics, the evolution of physics, if you look at how we progressed with our knowledge, is that the fundamental things that we have come up with historically, exactly as we discussed earlier, they actually have become more and more abstract. So we started with concepts that are very close to us and our intuition and even our physical makeup. So the concept of a force is extremely natural because we tend to push things, we tend to pull things. So it's very natural to think that there is an entity called force. But already with quantum mechanics, the fundamental entity is not force, it's energy. And that's already a more abstract entity. What exactly is energy? It's kind of harder to visualize and to understand than the concept of force. And with quantum mechanics, we've gone even much further than that. And that's what somehow suggests an intuition that maybe if we continue to extrapolate in this direction, we will ultimately go in a much more abstract um, domain, which to me looks like, at least at present, ought to be the domain of information. If you look at the axioms of quantum mechanics, I should add this. So there are many things that strengthen this kind of intuition. If you look at the basic rules of quantum mechanics, they sound almost like axioms of information theory. So they're telling you, Schrodinger himself used the language of information. He said quantum states are actually catalogs of information. And when I talked about Q numbers, they are also like tables of information. They are matrices, they have rows and columns. They are like catalogs of information. So it's very interesting that the immediate question for a physicist is to think that there may be something more fundamental even that goes beyond quantum mechanics and whose rules are completely just information theoretic in nature. So that's what I mean by that. Could it be that we can even understand everything in physics, not in terms of energy and exchange of energy, and in terms of how matter couples to energy and how matter couples to matter. But could it be that if we change the perspective and talk purely in terms of information, we could talk in terms of quantum states, but maybe there is something that goes even beyond this? To me, this would be fantastic. And actually, I wrote another book, Decoding Reality, exactly on this topic, that it's all about information processing.
Just to draw a picture, is this like if we could see with our eyes the reality beneath the physics, would we see numbers?
Right, so that's an interesting one. That's indeed the question. The question is whether we will even be able to ever directly see this reality as it is. I think we would see these collections of numbers. But again, it seems to me, at least in quantum mechanics, what's preventing us from that is the uncertainty principle. So it says that if you see one of these numbers, you automatically prevent yourself from seeing all of these other numbers. So if you learn the number that pertains to the position, you lost the information. You have to really acknowledge all of the other numbers that pertain to the velocity of the particle. And it seems to us that this is a fundamental limitation, that we cannot go beyond this limitation, which unfortunately would imply, as you said, that actually we will see maybe individual numbers, but we will never see the quantum numbers themselves, if that's the foundation of reality.
So is that because in base reality our eyes are also just numbers? What we
Yes, I
see with.
think exactly right. That I conclude this from this view that everything is quantum mechanical. And if you think that the machinery that's working in our eyes, that connects to the brain, that processes information in the brain, if you think that all of that is made up of the same quantum numbers, then this limitation is definitely there. Otherwise, of course, if this is if the brain is governed by different laws of physics, then you may be able to go beyond that. And in fact, that's why this goes back to the statement that I made that as soon as you make a hybrid description of reality, which is kind of half quantum mechanical and half something else, then you have to worry very much about how to put it together in a consistent way because it may lead to all sorts of paradoxes and violations of basic rules.
Is there any evidence that the brain is made up or are governed by different laws?
I would say no, because I think everything we've confirmed so far could be explained by the basic chemistry, and I think it's ultimately underpinned by quantum mechanics, which explains all of this chemistry. There are people again who claim that the brain could be performing operations that ordinary computers cannot perform. And already to me, this would be a big surprise. To me, this would be an indication, if this was true, and I don't even know how you would really prove that the brain really can do something that a computer cannot do. But if this was genuinely true, then I think one could more credibly suspect that there could be some other laws governing the brain. And this would be again surprising, like I said, because if you think about the evolutionary continuity, that it seems that life arises out of exactly the same non-living matter, and then it simply just gets improved incrementally by selective pressures. Then it's difficult to see how the brain would. Why would the brain obey different laws? It would be the question. Where would that come from?
Yeah.
Yeah.
So does this mean that the universe is in some sense computing itself?
That is a good view as well. I think I like that hypothesis that we should think of the universe as a really big quantum computer, really, ultimately. I think that's, and maybe the most powerful quantum computer in terms of the complexity and the size. When you say that, um, usually computer scientists would object. And the reason why they would object is because in order for you to have a computer, you really should demonstrate that you can program that machine as well. So the reason why, of course, we find computers useful and why we came up with the idea of a computer is that we can write software, we can write programs which we can feed into these computers, and then the computers can implement these programs much faster than anything that we can do. So it's an extremely useful tool. Now, you could imagine that we could program various natural physical systems, but you can see why this may become harder and harder to do. So when it comes to the whole, even if you take a simpler object than the whole universe, take a black hole, and sometimes people say the black hole is the densest object that we can imagine, so surely it would provide a far more powerful computer than anything that we have. And that may well be the case, but the question is, how do you actually interact with this object? How do you write a program which the black hole would then implement in order to execute the computation? And then how do you read it out?
Mm.
So it may well be computing something on its own, but to a computer scientist, this is not enough because I think you must be able to also program this object. So the question is, can we program the whole universe? I think, and that's for us to discover.
Yeah. So I guess this means that you think that mathematics is not something we invented, but something we discovered.
Now, that's also a very deep point. Um, it's difficult to know. Yes, I think it's difficult to know if we discover it. The question is immediately, where is this stored? So I think as a physicist, and I think most physicists would agree with me, it's unlikely. I think physicists don't believe in Plato's idea that there is this special world out there, which we call Platonic world, the world of ideas, maybe, of forms. Plato would call it the world of forms, ideals. And for him, he really thought that this world existed separately in the universe and it somehow interacted with our own world. In fact, Plato thought that our world is like a very bad imitation of the world of ideas. So I'm not a realist in terms of mathematical objects in this sense. I don't think that they exist in some special universe. But what it seems to me the right way to think about this is that the universe has the right laws of physics to give us the kind of mathematics that we discover. So probably the fact that, for instance, integers play a very big role for us, the fact that 1 plus 1 equals 2 and the basic rules of arithmetic have something to do with the fact that the world is quantum mechanical. So in that sense, you could argue that we are discovering mathematics in the same way that we are discovering different theories in physics. But I don't think that there is a container somewhere in the universe where all of these mathematical laws and mathematical theorems are really sitting independently.
I see. Just to ask you about the black hole you mentioned, what's inside?
Good question. Yeah. This depends very highly on the first question that we discussed of quantizing gravity, whether you believe that black holes are, for all practical purposes, really just classical objects, in which case the standard view of black holes is that anything that goes inside a black hole loses completely its own identity and just contributes to the entropy of the black hole. So the black hole grows as far as its degrees of freedom are concerned, but the state inside is so mixed that you cannot any longer tell what it is that went inside the black hole. So whether you put a table or a chair or an apple, it basically disintegrates inside to such a degree that it's unrecognizable. You will never be able to undo this information. And it's sometimes called information loss inside a black hole. Now, if you think that black holes, on the other hand, are quantum mechanical, then we know that there is no such thing as information loss in quantum mechanics. The laws of quantum mechanics are perfectly reversible. Anything that takes place in one direction can actually go backwards. It can be undone. You can always, in principle, reverse time. And if that's true for a black hole as well, that means that sooner or later, black holes ought to evaporate and they ought to radiate back exactly the kind of information, maybe in a different form. They could repackage the information to look different, but it could certainly never be lost if it's a quantum mechanical object. And I think to a physicist, this is a hugely exciting question, precisely because it's related to quantizing gravity. If information is not lost, then it seems to me we have no choice but to quantize black holes and to think of them as really huge quantum mechanical objects. But if, on the other hand, classical general relativity is correct, then maybe these are places where information genuinely gets lost and maybe even quantum mechanics gets violated inside a black hole.
Could black holes be a portal to another dimension or
That's
universe?
that's a nice thought as well, and many speculations. Yes. So there are these people who talk about the bridges between different bits of the universe, maybe even different dimensions, where you somehow have a portal where you enter through a black hole and then you exit through a white hole at the other end. Um, Called a wormhole. The object is called a wormhole. And it could be something, for instance, that's connecting bits of the universe that look very far apart from our own perspective. However, if we understood that there was a tunnel of this kind, we could actually end up in this part of the universe much more quickly. So I think there is nothing to suggest that this is not also possible. Again, we have no evidence of anything like that in astrophysics, but to me, it would be fascinating if this was true.
Before I let you go, I have to ask you about time. What
Of
is
course.
time? Does it exist?
Yes, these are all very fundamental questions. What is time? In physics, I think we are very, as you know, we are very pragmatic about time. So the way that this comes from Einstein, right? Einstein was the person who introduced these notions of clocks and different observers carrying their own clocks and then comparing these clocks, which is how he phrased the whole of his theory of relativity, special relativity. Uh, so if you look at the way physicists approach this question, we never think about measuring time directly. So as far as a physicist is concerned, there isn't such a thing as time underneath. What is happening is that there are dynamical processes in the universe, and we are simply comparing one rate of change in one object to another rate of change in another object. I mean, even when we measure as humans, even when we measure time, originally we thought about the motion of stars and different planets, and that was the notion that told us about how much time advanced, when we need to take care of certain things and stuff like that. Even if, as we started to make more and more sophisticated clocks, our atomic clock, all it does really, it counts how many times an electron gets excited and de-excited in an atom. So what you're really measuring is the position of an electron inside an atom, and the position changes extremely rapidly. It's much faster than any other clock, but you are never really measuring time directly. There is no sense in which you are actually coupling to time as an independent object. Also, when we look at the clock, of course, what we are looking at is the positions of the hands of the clock. So it's always one position against another position, and that's what we call time. To me, this suggests that there isn't such a thing as time, that we should always talk about time in this relational way, one thing relative to another thing, rather than that there is something that really flows at the constant rate, the way that Newton thought about it, for instance.
Because I read someplace not long ago that we should more look at it as a change in a system's condition
Yes,
rather than time passed by.
yes. It's more exactly. I think it's a little bit how Aristotle himself thought about it. Certainly, people like Leibniz also thought about it in this relational way.
What about entropy in yeah, speaking about time, entropy.
Yeah, good. That's a very natural question that you're asking because in the second law of thermodynamics tells us that entropy of the universe always increases. And you could say, well, if that's true, isn't this like the best possible quantifier of the change in the universe? And frequently people even talk about the arrow of time being the increase in the entropy of the universe. To me, again, and I think this is linked to our previous discussion, to me, this is just an indicator of the fact that so I don't think this is, if quantum mechanics is fundamental, I think the entropy increase is not a fundamental law. If quantum mechanics is fundamental, then entropy of the whole universe always stays the same. It never increases and it never decreases. The total information in the universe is always constant. So it cannot be created, it cannot be destroyed, which would mean that this arrow of time is not fundamental. It's kind of a superficial thing that we observe simply because we don't have the perspective of the whole universe. For us, for instance, when radiation leaves a certain system, we think of it as the entropy increasing. We lost the information about this radiation. Whereas in fact, if you think at the level of the whole universe, the information, and again, if quantum mechanics is the right way to think about it, the information is really never lost. It's always there. So somehow it seems to me that this arrow of time would not at all exist in the quantum universe. So this wouldn't be a fundamental way of talking about time.
Lastly, then, is it possible to do your work without asking yourself the big philosophical questions?
Very difficult because I think you come up against these things all the time. And the tricky bit is, as you know, for a physicist, the tricky bit is to really always try to convert them into a practical experimental question. So even when I think about interpretations of quantum mechanics, there is the Copenhagen interpretation, there is the many worlds interpretation, there is the hidden variable interpretation, all sorts of interpretations. And by their very nature, people say, well, they're just interpretations. They agree about all of the observable facts. But in fact, that's exactly the interesting thing, to push them as far as you can to the domain where they might start to disagree. And that's where it becomes interesting for a physicist. So physicists somehow should understand all of these philosophical issues. But I think as physicists, we should be able to go beyond that, extrapolate them, and then see how different interpretations lead to different experiments, and then test them and see whether something interesting happens there. But the line is very blurred. There isn't a strict line between physics and philosophy.
Last one, then. What is the meaning of life?
I think when you ask a physicist this question, probably we're just as clueless as anybody else. Um, Difficult to tell. Of course, each of us has a strong sense of meaning in our own lives. But you can easily argue that this is just a meaning that's relative to us. And it can be explained rationally through even evolution, let's say, why we care about certain things. Because of course, all of us humans, even when we are very different from one another, we seem to have a set of things that really we care about a lot. They make us happy, and they give us meaning, as you say, to what we experience. But as a scientist, if you lift yourself above that, it would seem that there isn't a more absolute way of talking about the meaning than this. It seems to me it always has to be phrased with respect to ourselves. And it's clear that then we can easily discuss this. And I think this is a very important topic for our lives. But at the level of the universe, if it's really true that life simply arose by some accident out of inanimate matter, it's very difficult to ascribe any kind of higher level meaning to the universe as a whole. I think it only carries the meaning that we ourselves attribute to it. I don't think there is a more fundamental meaning.
Vlatko, thanks for a very informative conversation.
Thank you very much, Alexander.
Tusen takk for at du hørte på Bendiksen Airways. Dersom du har tips, kommentarer eller vil gi en vurdering av episoden, så gjør gjerne det. Det setter jeg stor pris på.